for a crack, what is established now is that the stresses follow a factor which is common and and you have a root R singularity. Okay. And we also know that it will become infinite as you come to the crack tip. Okay. So if this is the crack, then here the stresses exactly at the tip will be infinity. Okay, this part we have understood. We have also seen some examples of superposition that we will use today in the second part of the lecture. So theoretically, this is what George Irwin arrives at, and then theoretically it is telling that the stresses are infinite, which can't be. Okay. So before stress goes to infinity, if the material is very brittle like Griffith's material, then it is going to fail. So crack will be propagating, and that situation will never arise where you can have an infinite stress. Okay. But even then, even if the crack is not propagating, even if I apply like 0.1 megapascal or 0.1 pascal of stress on a metallic material, do you think there will be a plastic zone? On steel, if I have a crack of, let us say, 5 millimeter, and the amount of stress which I apply is 0.1 pascal, do you think there will be a plastic zone?
No.
Yes. There will always be a plastic zone. Any finite value of stress, and if there is a crack, there will be a plastic zone, and we will see how that is coming.
Sir, will it not depend on yield stress?
No. If there is a yield stress, if the material is going to deform plastically, there will be a plastic zone.
I mean, without crossing the yield limit.
Yeah, I don't understand the question. Say it again.
I mean to say, if the steel has a particular value of the yield strength, if the applied stress at the crack tip is crossing the yield strength, then we will observe the plastic zone.
No. Whatever stress you apply, however small it will always reach infinity. So, infinite amount of stress is always higher than yield stress, whatever is the value. कोई भी वैल्यू हो, ब्रह्मास्त्र भी बना लोगे तो भी उसका भी जो yield strength है वो क्रॉस तो हो ही जाएगा, infinite से ज़्यादा तो नहीं हो सकता. Okay, so however small, but there will be a plastic zone. So that's why when people do modeling of brittle fracture in a steel, it is always slip-induced fracture which is modeled. So that means there is always some amount of plasticity which is assumed. So, well, we will discuss brittle fracture and how we model that. So there we'll see that there is a threshold value, and that threshold value signifies that you must have some amount of deformation. It can't be zero. So you can't have a situation where brittle fracture can happen at zero stress. That cannot happen. Or even very small value of stress, it cannot happen. You need some amount of deformation, however brittle the material is. Okay. So here on this line, I have theta is equal to 0. Okay. And the stresses are going infinite. So somewhere it will be crossing the yield strength of the material. Okay. Why going there? So maybe here, whatever is the value of yield strength, it will be crossing that. Okay. So because of that, the stress conditions will now be modified. It cannot have the same profile. But before we do that, let us say that there is a, so let us say this is the part where the plasticity begins. Okay. And now what Irwin does is he assumes that this plasticity is going to act as if the real crack has grown virtually, not really. Do you follow? So there is some plastic deformation here, okay? The area can be of any shape, but there is a plastic deformation which is happening. This plastic deformation would act as if the crack length has increased, not in reality, but it will be equivalent to that. क्या लगता है, सही है गलत? So if the material is ductile and there is some plasticity, so that means this area, this crack will be blunting, right? It will get blunt when you open up. It will not remain sharp, right? Is this okay? नहीं okay नहीं है? Okay है? तुम्हारा मेरे को समझ में नहीं आता okay है कि नहीं है? होगा मुझे पता ही नहीं है हाँ okay so then like we can do something इसको निकालो और इसका एक सैंपल बनाओ और उसमें क्रैक डालो ये सैंपल है मान लो और इसमें क्रैक बनाओ कैसे बनाओ कोई स्केल वगैरह है तुम्हारे पास नहीं है अरे ऐसा नहीं करो नाखून का नहीं बनाओ किसी के पास रूलर है स्केल है चाबी it will already be blunt make crack बन गया ठीक है इतना ठीक क्रैक बन गया अभी इसको खींचो तोड़ना नहीं है हाँ तो क्या हो रहा है अभी क्या हो रहा है श्रिंक हो रहा है साइड से वो तो मैंने पहले बताया था
और वो क्रैक मतलब
क्रैक का कर्व बन गया नाउ डू यू डाइजेस्ट अभी भरोसा हो रहा है कि मैं जो बोल रहा हूँ सही है कि नहीं so last time what we discussed you will also see sinking from the lateral side and if you just instead of pulling like this if you pull it like this you will also see and the backward side there will be a bending okay that you can try so this blunting can be taken as a sharp crack which has opened up via certain distance so this really hasn't opened this has blunted the crack has blunted it has not grown okay but it is equivalent to a sharp crack which is extended to certain amount do you follow तो आप ये बांट के सबको दे दो सबको ट्राई करो देखो क्या होता है
सर
हाँ
हम इसमें स्मॉल कोई भी फाइनाइट अमाउंट ऑफ स्ट्रेस मतलब इनफाइनाइट स्ट्रेस पे क्रिएट करेगा सर तो सर इंटरमोलिकुलर फोर्सेस में भी स्ट्रेस होता ही है मतलब
वो रियलिटी नहीं है well you finish your question
सर एक सॉलिड के अंदर जो मॉलिक्यूल्स होते हैं मतलब इसके सराउंडिंग में मॉलिक्यूल्स हैं वो भी कोई डिफरेंट फोर्स लगा रहे होंगे वो भी स्ट्रेस क्रिएट करेंगे तो मतलब एनी मूवमेंट जो इनफाइनाइट स्ट्रेस पे रहती है किसी भी मूवमेंट में
हाँ
हम स्ट्रेस लगाए ना लगाए
नहीं लगाएंगे तो कैसे there will be no stress intensity factor
जो
सिग्मा रूट पाई में सिग्मा है ना
सर हमने नहीं लिखा ना इस सैंपल हमारा कोई क्रैक
अच्छा so you have molecular stress so you are saying because of that there will be
so फाइनाइट अमाउंट कोई भी सर आप बोले भी मिनिमम कोई भी अमाउंट
हाँ
तो फिर वो भी इनफाइनाइट स्ट्रेस पे होना चाहिए
करेक्ट
उससे क्रैक प्रोपेगेट नहीं करता सर उससे बेटर वैसे रियलिटी में तो नहीं करता
रियलिटी में इनफाइनाइट हो ही नहीं सकता इनफाइनाइट स्ट्रेस हो ही नहीं सकता अगर so for example for whatever reason if on the crack tip you can have infinite stress this also tells you and material is not breaking them so this also tells you any material can take infinite stress because we have not made any assumption about the material it can be steel it can be wood it can be plastic it can be anything so any material should be able to take infinite stress बस करना क्या है क्रैक डाल देना है right so then we should be drilling holes in all the bridges and everywhere so that it can take infinite stress. आर्मर बनाने की जरूरत नहीं, क्रैक डाल दो तो सारा बुलेट ऐसे डिफ्लेक्ट हो जाएगा. But ये reality नहीं है. Theoretically it is saying that it reaches infinite stress theoretically. And this calculation and derivation is coming from theory of elasticity. No material is truly elastic, right? No material is truly reversible. They don't deform. None of them deform to infinite stress in a reversible manner. So there is going to be some deformation which is irreversible. And because of that, this infinite stress is going to be truncated at some point, which we are calling yield stress. Okay? So suppose that this is where the virtual crack extension happens. Okay? And because of this virtual crack, I will have another plastic zone for this virtual crack. फिर तो ये कहानी बढ़ता ही रहेगा, but we will stop here. Okay? So now let us say that this distance is delta and this distance is lambda. How much is the stress here? Maximum at the tip when r is equal to 0? Sigma ys. Okay? So there I can write sigma ys is equal to k divided by root over 2 pi. What is the value there? Lambda?
Yes, sir.
And this k will be sigma root over pi into a plus delta. Is it okay? Because that stress intensity is coming for the crack A plus delta. Is it okay? नहीं? हाँ ले एक मिनट. 1, 2. See, I'm saying, I don't know, where did you lose me? कहाँ से नहीं समझ में आया? लग गया? चल. Okay. So from this relation, I can write lambda will be equal to what? So sigma by sigma ys, and then what will happen? So pi will cancel out. This pi is gone. I take lambda there. Sigma ys comes here. Okay, so this will be sigma by sigma ys whole square into a plus delta divided by root 2. Okay, so lambda will be equal to 1 by 2 square, and then I have a plus delta, right? Now what do we do? That let us say for this virtual crack a plus delta, the modified stress because of this delta amount, because of this virtual crack extension which has happened. So this stress profile is for A. Okay? There will be a different stress profile for A plus delta. Okay? So for that, maybe the stresses are going infinity here. Right? And I'm saying that that cannot happen, and that is compensated by plastic deformation. So let us say here sigma ys happens. Now what do I have to do? I have to compensate for this amount of area with this amount of area. Right? The stresses which are going to infinite must be accommodated by the plastic deformation. So this shaded area must be equal to that. Okay? So let us call this area A and this area B. So what is A? Or what is B? Let us see. So B is simply sigma ys into delta. And A is equal to what? Integration from 0 to lambda k by root over 2 pi lambda or r dr. That's the variable here. So this integration will be this area also. This plus that will be that integration. So I have to subtract this part. So that will be minus sigma ys into lambda. Is this okay? And I'm saying that b is equal to a, so that should be equal to that. Okay? So then I can take this term on that side. So I'll have sigma ys into delta plus lambda. This will be equal to integration of 0 to lambda, and k is sigma root over pi into a plus delta divided by root over 2 pi, and then I have 1 by root r dr, and 1 by root r dr will be 2 root r. So I will have 2 root r, and this will go from 0 to lambda, and this will go away, right? So then what do I have? So pi is gone, okay? And then I can assume this, that delta in comparison to the initial crack length is very small. So this part is very small in comparison to the initial crack length, so I will ignore it. That's why I am assuming it. So now I will have sigma root over a divided by, so this is root 2, so it will become root 2 on the numerator, and I will have lambda here, right?
Yes, sir.
So this is equal to that. Okay?
Yes, sir.
So now if I write, so I take sigma yx on that side, so delta plus lambda is equal to sigma by sigma ys into root over 2a lambda, okay? And then I square it because I can, so this will become square and the square root will go away, okay? So sigma by sigma ys whole square must be equal to what?
Delta
2 lambda by a, because I am ignoring delta, right? So that will be 2 lambda, or sigma by sigma ys whole square into a. Do I have a also? Sigma by sigma ys whole square into a I have, right? So that will be equal to 2 lambda, right? So I can remove this and I can remove that, and I can write 2 lambda into 2 lambda, which becomes 4 lambda square. देखो इसमें response मिला मेरे को, okay? Then I drop this square now, okay? So lambda plus delta is equal to 2 lambda. What does that mean? Delta is equal to lambda. Okay?
Sir,
Yeah?
sir, this is the theory of LEFM, linear elastic fracture mechanics.
Okay.
So, but why we are considering here the plastic zone? Why not we am saying the elastic zone this is?
What?
Sir, delta is saying plastic zone is forming at a tip. Why I am not saying this is the elastic zone? Because we are studying on linear fracture mechanics here, na?
What is elastic?
We are considering
Everywhere
that is-
there is elastic deformation.
yeah.
There is no particular zone where elastic deformation will happen.
Okay. So initial consideration I am talking about कि when
देखो ये
this theory.
शास्त्र नहीं है कि यहाँ पे नाम रखा हुआ है इस हिसाब से
Mhm.
कि जो नाम में है उससे हमको सब पता चल जाएगा.
But sir, this is only valid in the elastic region, na? K upon 1 upon under root 2 1 upon root r.
Yes.
That is only valid for elastic.
Yes.
So that's why I'm saying ki why saying here is a plastic zone and this is valid for that.
So I'm saying there is a plastic zone because stresses cannot reach infinite
Okay.
and material will deform plastically. So at some point you will cross that value, and beyond that value stress will not increase, assuming the material is ideal plastic. Okay. So if for the material stress strain diagram is this, then beyond sigma ys stress is not increasing. Okay, in that case I will have this kind of profile. Okay, A is equal to B. But in reality, this can strain harden. Okay, so stress will increase after yielding, but it will never go to infinite value. Okay, so we are considering that plastic deformation is happening. There is no, so linear elastic fracture mechanics. First of all, you are considering linear elasticity, so this is not valid for non-linear materials.
Yeah.
And then what is the assumption which we have made to drop delta? That delta is very small in comparison to A. Okay, so it is so small that it is ignorable. When that is true, then we have dominant elasticity.
Yeah, understand.
Even though there will be a reason where the stresses will go beyond UTS also. And we don't really know what is happening following this theory. We don't really know what is happening there. So this derivation is for this kind of stress strain diagram. Okay, steels or any other alloy will not show this kind of stress strain diagram. So then the complicated solution will be that you have something like this area, and that has to be compensated by the other area which you are dropping. So this area must be equal to this area. But rather than doing that, some people do what? They take the worst case and assume that plasticity begins beyond UTS. And some people are very moderate. They take an average of sigma ys and UTS and they compensate for the strain hardening part. It will work because I am assuming, and all these things are for those materials which are deforming plastically but not very significantly. So this is not true for a very ductile material or a material which is very thin, which is in plane stress, for which plastic zone is very high. Okay, so this plastic, and this you must remember that we have dropped delta, and therefore we have a condition that the plastic zone which is forming must be very, very small. How small, we don't know that, but it should be significantly smaller than the initial crack length. Only then whatever Irwin is doing is valid. Okay, so delta is equal to lambda tells that the first approximation. So we have assumed that there is a plasticity here, and then there is a plasticity which is equal to lambda. So delta is equal to lambda. So then we can consider a circle which has a value of lambda, and that is deforming plastically. कुछ गड़बड़ हुआ इधर? नहीं, सब ठीक है ना? Okay. Okay. So so there are other people who also tried solving this problem. So I'll discuss one more which is famous and known as Dugdale model. It is also known as stripped yield model. Okay, so Dugdale also does the same thing, and all these things has happened for central cat panel, not for edge crack panel. So not for the edge crack, for the central crack. The derivation, it doesn't matter. So in Dugdale's case also, you have a crack which has a length of 2a. And this is there in fracture mechanics. Whatever formula we are using, if in a numerical problem, in exam or anywhere else, if you are given a problem where the crack length, let us say for a central crack panel, in the problem it will not be drawn, it will be written that you have a 5 millimeter through thickness crack in a center, in a sheet or in a plate at the center. When that is written, then in all those formula you are supposed to take 2.5, not 5. Okay, and then you have a side crack on the edge, then you are supposed to take the whole crack length because that is half of it. Okay, so Dugdale also starts from that, and then he says that you have again a virtual crack extension because of plasticity. Okay, so you have a zone here which is plastically deforming, and because of that you can imagine the crack to have grown by a certain amount. So delta A on this side and delta A on that side. Okay, and because of theory of elasticity, whatever stress intensity factor is coming on this new virtual tip must be compensated by the yielding which is happening. This is what Irwin is doing, this is what Dugdale is doing. Okay, so on this virtually extended crack, whatever stress intensity factor is coming, that must be compensated because the crack has not opened up. The crack is not opening. That's not a real crack. So who is not allowing this crack to not open? That is yielding. Okay, it's not true. There is no compressive stress there, but Dugdale assumes it. Okay, it's a trick which Dugdale does, is that because of plasticity we can assume the crack to be extended by certain amount, and this crack is virtual, this is not real, so something is holding this, and that holding is because of yield strength, because ideal plastic material is there, so stress cannot go beyond yield strength, so stress available is yield only, and that is holding this material intact and it is not allowing it to grow. This is not the reality, it's a trick which Dugdale applies. Okay, and he says that the stress intensity factor which is coming here must be equivalent to a stress intensity factor as if there are stresses which are compressing it and holding the two materials together for only this amount. Okay, is it okay or not? So don't get confused. The real stresses are not compressive. Okay, nothing is compressing the crack. Dugdale is imagining. Okay, these days anything we say people take it controversially, but you can imagine that Dugdale is high and he is just imagining, and this happens in science. Okay, you don't need to really get high, but you can just, if you are thinking about any problem, a lot of so you are like, so when I was doing my PhD, I used to write some codes and solve some problems, and wherever I am, when I'm traveling also, I'm thinking about that code, I'm thinking why that is not working, what is going wrong there. So one aspect is when a code is not giving you any result, it could be because of the syntax error, it could be because of the loop or whatever, somewhere you're doing it wrong. It could be because you're catching the physics wrong. Okay, so so that's what Dugdale is doing. So in my master there was a project which I was doing in Darmstadt, and that was on helical compression springs. Okay, so you have springs, these are helical springs, and tension spring will be closed. Okay, so then you can open it up, and compression springs are this which you have in your dot pens. Okay, so this I was supposed to model, and I modeled for the first time, and I had to find out the shear stress on the inner side. So this is really not a line, it's a wire. Okay, so it has certain diameter. Okay, so I was supposed, and because on the inner side you will have maximum shear stress, so my job was to find out maximum shear stress wherever it is. Okay, so I did that for the first time, and I got something like this. So maximum shear stress was oscillating in the coils, and then it was going down at the ends. This is what I got, and then my professor said, why are you getting oscillations? Because theoretically it shouldn't be. Theoretical solution was this. Okay, so when people ask questions, sometimes they really are asking. They are not doubting your calculations, they are really asking. And because of our brought up and other things, I imagined that I'm wrong. So I thought the stresses shouldn't be like this. And for next 6 months, I devoted myself to find out that the stresses must be like that, because we know that theoretically it should be like that. And it never came out to be like that. And then there was a meeting from Bosch and other companies, and they said, no, your calculation is wrong. You're doing something wrong. So if it is oscillatory, the question was why oscillations are coming, why stresses are increasing and decreasing. Okay, and modeling did not help, theory did not help. What helped was to look at these springs, and this is for fatigue. So when you are pressing and losing and pressing and losing, then what is really happening on the spring? So when I looked at the springs in the testing machine, then I saw that they are jumping. Okay, and why are they jumping? So the load has to be exactly on the axis. When that happens, you will get this. But it can never happen, because somewhere you will cut the spring. So center of mass will never be on the axis. So it will always have a tilt. Okay, and because of that it will always jump, and because of that you will always have oscillations. So the further confirmation was that if this thing closes up, then I should have less oscillations, and that was confirmed. So sometimes thinking helps, but in order to think, you really need to think, or you really need to see physically what is happening. And at certain scale we lose that thing. We cannot see beyond a scale. We cannot see atoms, we cannot see quarks, and also we can't imagine there. So there only calculation works. Whatever is the reality is open to interpretation. So Dugdale is doing that. Okay, so now what do? We find out, so there will be a stress intensity factor because of the virtual crack, and that will be sigma root over pi into A plus delta F. Okay, and this must be compensated. So tensile stress intensity factor and compressive stress intensity factor, which is coming because of the compressive stress, must be 0. That should be balanced, right? This is what Dugdale is doing. Do you follow?
Yes, sir.
So K1A is okay. What is K1B? So for K1B, you need to, well, there is a straight formula. I am not going in derivation of that. And that is if the crack is from, well, so if the crack is from minus A to plus A, where A is the value of x coordinate. So x is equal to A, x is equal to minus A on the other side. So in that case, this is minus A to plus A plus x by A minus x root over that dx. And then whatever is the stress you have applied, pi A. This is the stress and intensity factor for this kind of scenario for a distributed force. So that distributed force is in the form of stress here. This is not in Newton, this is in the form of megapascals. Okay, so if you have distributed load, And if that load is F, then F into whatever distance you have, area you have, that will be P. Okay. So this will be K1B, and then we can play for how much time do I have? Or we had
10 minutes.
So if I'm going from minus A to plus A, then this I can convert by using odd and even function. And if it is an even function, then I can write 2 and then I can do that, right? So then I simply write 2 and then I change it from 0 to A, and I will have to add f of A plus f of minus A. So that will be root over A minus x by A plus x. Okay? Dx. So then what it will be? How much this will be? What? Say it again.
2a upon a square minus x square.
2a upon
Root over a square minus x square.
a square minus x square. Right? Integration of that from 0 to a dx. Is this what you are getting?
Yes, sir.
Do I need to have half also? No. I have already multiplied with 2 and then I am getting 2. Oh, fine. So, but I am not sure if there was a 2 here. I think this 2 is coming extra. Okay, but we'll deal with this. So now what I have to do is, I have to change the limits from A to A plus delta A, because this thing is happening only on this part. Only on the end which is plastically deforming. Okay? So now I have root over pi, and this also I will change to A plus delta A. And then the upper value will also change to A plus delta A.
Upon under root.
And then I will have, so this I can take out, and then I will have integration of dx divided by root over a square minus x square from a to a plus delta a. And instead of a, I will have a plus delta a here also. Okay? Well, how much was lambda in Irwin's case? Lambda was 1 by 2 sigma by sigma ys whole square into what was that? A plus delta?
Yes, sir.
So this delta I can draw. So if k is equal to sigma root pi a, then k square will be sigma square pi a. Right?
Yes, sir.
So this is k. So I can write sigma square pi a divided by 2 into sigma ys whole square. Then I have to put another pi. So then it will be equal, no? So pi sigma square a sigma y, right? So this I can write as k1 squared divided by sigma ys squared, and then I have 1 by 2 pi. So this is the radius of plastic zone in case of Irwin for plane strain or plane stress. So this is for plane stress condition. And for plane strain, you will have a smaller plastic zone, because in plane strain you have more constraint on the material. The stresses are higher, so material will deform plastically, but to a very small size. Okay. So if you have too much constraint, material cannot deform so easily. That's the way you should look at it. Okay. It also happens in reality. So like if you have a Fevicol very thin layer between two strongly holded things, then because of constraint, this soft material will act as if they are very, very strong. The strength is not really coming from this soft Fevicol or the glue which you have put. The strength is coming because of the constraint which you have from both sides, which is asking for this glue part also to maintain the same amount of strain. So that is not allowing this glue part to move. Okay. This also happens in steel. There was an example where an interstitial free steel was forged with high carbon steel on both sides, and the interstitial free steel has no interstitial. So here you can apply that concept. नाम से infer करने का. So interstitial free steel has no carbon, no boron, no nitrogen and things like that. Not no, but in ppm levels. So the voids are very empty. And you can't have those phenomena where pinning of dislocations can happen because of interstitials and all those things. So interstitial free steels are very, very ductile. Okay. And when this was done and it was broken and looked in SEM, and we'll talk about the signatures of brittle and ductile, the signature in this part, in IF grade part, was representing a brittle fracture at room temperature. Okay, so there was too much constraint here because of the high carbon steel. That is one reason. Another reason could be that you are creating a gradient of carbon. You have high carbon steel and then you have interstitial free steel. So you will have a and you cannot stop interstitials from diffusing. So they are ready to go. So depends on the calculation. They could fill it up with carbon, or there can be a zone where you have a lot of carbon which makes it very brittle. That could have happened. Another thing was the constraint from the both sides, which is making IF grade steel also very brittle. Okay, so that is that. And then we have integration of this. So we have 2p, so 4p. And then what do we have? So this root will cancel out. So I will have root on the upper side, a plus delta a divided by root over pi I will have. And then integration of this will be what?
Sine inverse.
Yes. तुम्ही submit था. Sine inverse a by a plus delta a, or not?
Yes, sir.
X by a plus delta.
X by
And then we have to put the limit from a to a plus delta a. Okay. So then we will have AB is equal to 4p divided by root pi. I don't know why 4 is coming. Should have got just 2 divided by a plus delta a. And then I apply the limits. I will have sine inverse of a plus delta a by a plus delta a is 1.
Yes, sir.
Minus sine inverse of a by a plus delta a. So that becomes 4p by root over pi, and then this is 90 degree minus sine inverse theta is cos inverse theta. Okay, so then I will have root over a plus delta a cos inverse a by a plus delta a. And now I apply P is equal to negative of sigma ys, because that is compressive. That is what Dugdale is assuming. Okay. A plus delta A cos inverse A divided by A plus delta A. And this must be equal to what? No, not this must be. So this plus A1 is sigma root over pi into A plus delta A. This is equal to 0, right? here. So that means this is equal to that. Okay. So अभी a plus delta a गया, क्या बचा? So then I do sigma by sigma ys, sigma divided by sigma ys. What else do I have? 4 also will come here. Pi will come up. Is there anything else? No, pi. So root pi will become pi. So sigma pi divided by 4 sigma ys must be equal to cos inverse of that. So cos of this will be equal to a divided by a plus delta a. So what do we have? A divided by a plus delta a is equal to cos, sorry, not inverse now. So we have sigma pi sigma divided by
4 sigma.
4 sigma ys. That's it, right?
Yes, sir.
And then I can write sec of this will be that. So a plus delta a
By a.
divided by a, which is equal to 1 plus delta a by a. Right?
Yes, sir.
And then you do the expansion of sec. So sec of x can be expanded as 1 plus x square by 2 plus x to the power 5x to the power 4 divided by 24 and blah blah blah. Okay? So then I am not taking anything beyond x square because of obvious reasons. So this is sec of x. So then I will have 1 plus delta a by a equals, what will I have? 1 plus pi sigma by 4 sigma ys whole square and 2 also will come. Right?
1 by 2.
So 1 and 1 there is no meaning there. So delta a will be equal to pi square sigma square a divided by 32 again. 32 sigma ys whole square. Okay. Somewhere I made a mistake which I am not able to find out. So this, instead of 4 I should get 2. I don't know where was that mistake. I don't really know. So here we did, why did we do 2p? Because this was an even function. No, this is wrong.
Yes, sir.
This is wrong. When I'm adding these two, so a minus x by a plus x, then I don't need to do 2 here.
Yes, sir.
So when you have an even function, then integration of minus a to a f of a is equal to 2 of f of a. Why? Because you actually add f of a plus f of minus a.
Yes, sir.
And because this is even, it becomes f of a. So it becomes 2f of a. Okay? So I did it twice. So when I'm really adding this, then I don't need to write 2 here. Okay? So this will be 2. So 2 square now will become 4. 4 into 2 will become 8. Okay?
Yes, sir.
So delta A, and what is delta A? Delta A is the plastic zone radius.
Yes, sir.
Okay, that is the virtual crack extension. So then I have RP, which is delta A, is equal to how much? Pi square sigma square A divided by 8 sigma ys squared. So then I can write sigma square pi A. So sigma square pi A will be k, right? So I will have pi extra.
Yes, sir.
Then I can write k1 square divided by 8 sigma ys square. So this is pi by 8 K1 divided by sigma naught whole square. This is the plastic zone which you get when you apply Dugdale's model. And from Irwin, what you are getting is Rp is equal to 1 by 2 pi K1C or K1 by sigma naught whole square. So how much is pi by 8 really? Can you calculate? अरे कहीं कर लो कैलकुलेटर फोन नहीं 3.14
0.392.
how much
0.392.
so this is 0.392 and this thing and how much is 1 by 2 pi
1.57.
what
1.57.
what
9.
हो ही नहीं सकता
2 into
1 by 6 है ये approximately
0.16.
is it correct 0.16 so approximately you have a difference of double in Dugdale's model and in Irwin's plastic zone model but plastic zone really falls somewhere in between plane strain and plane stress condition so it is somewhere in between 1 by 2 pi and 1 by 6 pi for plane strain you get 1 by 6 pi and rest of the things remain same so the plastic zone will be somewhere in between and the real plastic zone in 3 dimension will not be as simple as what Dugdale and Irwin have done. So when you have mode 1 loading, that means you are opening up and you have a thickness. Then the plastic zone shape, we will see how that develops. So the plastic zone really looks like this. It's not a circle in mode 1. It is a circle in mode 3. Okay, in mode 1 it's not a circle. The shape is of this size. So on the other side also it will be of the same size because of symmetry and inside it will decrease. The plastic zone size will decrease because on the surface you always have plane stress condition and at the center as you go in the center you have plane strain condition. Okay, so it's like magnet, you can't find north pole, south pole. So there is no complete plane strain or plane stress condition, it's a relative thing and we always have some area which is associated with plane stress and plane strain. Okay, so I believe the time is up, so we'll end today here.